Welcome back. Today we're going to look at section 4.4. We're going to focus on the first two learning targets today, using like bases to solve exponential equations and using logs to solve exponential equations. And then for the next few days we'll tackle these other couple learning targets. So for today, our first one is to solve by making the bases the same. We're looking at exponential equations, meaning the variable that we're trying to solve for is an exponent. And there's one type that's fairly easy to solve if you can get them to have the same base. So when I look at this first example, I see 2 being raised to a power, and on the other side of the equation I have a 16. If I think of that as 2 to a power, I can then set the powers equal. In other words, if we said 2 to some base x, 2 to some power x equals 2 to another power of y, then x and y would have to be equal. All right, so if the bases are the same, in this case they're both 2's, then the powers would have to be the same. So I'm going to think of this 16 as 2 to the 4th power. And now I have 2 to the 3x minus 8 equaling 2 to the 4th power. And now my powers have to match. So 3x minus 8 would have to equal a 4. And now it's just a linear equation to solve. So I'm going to add 8 to both sides and then divide out my 3. And remember, you can always check your work by plugging that answer back into the original equation. So if we put 4 back in, 3 times 4 is 12, minus 8 is 4, and 2 to the 4th is 16. So it does work. All right, looking at the second example, we have 27 to the x plus 3 equaling 9 to the x minus 1. In this case, we're going to have to convert both sides because 9 and 27 both have a common base of 3. So 27 is 3 cubed. So 27 to the x plus 3 would be the same as 3 cubed to the x plus 3. 9 is the same as 3 squared. So we're going to have 3 squared to the x minus 1. And when you have a power to a power, so we have a power here raised to another power there, then we multiply the powers. So we end up with 3 to the 3x plus 9 equaling 3 to the 2x minus 2. And again, if we have common bases, in this case they're both 3's, then we can set the powers equal to each other. So 3x plus 9 has to equal 2x minus 2. And again, it's just a one variable equation that we can solve. Subtracting 2x from both sides leaves me an x on the left. Subtracting 9 from both sides leaves me negative 11 on the right side. So x would have to be a negative 11. All right, for example 3, we have 5 to the 3x minus 6 equaling 125. We can think of 125 as 5 to the 3rd power. So now we can set our powers equal since our bases match. So 3x minus 6 has to equal a 3. Adding 6, we've got 3x equaling 9, so x must be a 3. All right, go ahead and pause the video and try number 4, and then turn the video back on when you're ready. All right, let's check how you did on number 4 here. An 8 and a 4 both can be written as 2 to a power. 8 is the same as 2 cubed, and 4 is the same as 2 squared. So I'm going to rewrite the left side as 2 to the 3rd is being raised to the x plus 2. On the right side, I have, instead of a 4, I'm going to put 2 squared. It's being raised to an x minus 3. Power to a power, again, we have to multiply these. So we have 2 to the 3x plus 6. On the other side, we end up with 2 to the 2x minus 6. And then setting those powers equal to each other, 3x plus 6 has to equal 2x minus 6. Subtracting 2x, we have 1x. Subtracting 6 from both sides, we've got negative 12. So x would have to be negative 12. Now we're going to do the same thing on these next couple. They just look a little more complicated. In this first one, we have 9 to a power that's a fraction, x minus 8 divided by 4. On the right side, we have the square root of 9. But remember, we can think of that as 9 to the 1/2. And so now we can really set those powers equal to each other. X minus 8 divided by 4 has to balance with 1/2. It is a proportion. We can cross multiply, or we can think of timesing both sides by 4. The 4's cancel on the left side. We've got x minus 8. On the right side, half of 4 would be 2. And so x would have to be 10. All right, for question 6. 27 to the x equals 1 divided by the square root of 3. Let's clean up the right side first. The square root of 3 we said was 3 to the 1/2. But to get it out of the denominator, we can move it to the numerator and make that power negative. So 3 to the negative 1/2 is equivalent to 1 divided by the square root of 3. On the left side, we can think of 27 as 3 cubed. It's being raised to the x power. So now our powers have to be equal. So 3x would have to equal negative 1/2. Dividing both sides by 3, we end up with x being negative 1/6. Okay, similar idea here in number 7. 1 divided by e is the same as e to the negative 1. We can use a negative power to cause that to be the reciprocal. Instead of 1 divided by e, we just get e. Powers have to match now, so x plus 9 has to equal negative 1, so x would have to be negative 10. So those first 7 examples, we were able to get both sides to have the same kind of base, and then it's just a matter of setting the powers to be equal. The second half of our lesson here is looking at examples where we can't get common bases. In other words, 4 to the x equaling 15. If it was 4 to the x being 16, I could get a common base. But I cannot write 15 as a power of 4. So we can do this using logarithms. We can take the log of both sides. So I'm going to actually show you 2 ways of thinking about this. I could write log using base 10, so just common log of 4 to the x equals the common log of 15. So I've taken the common log of both sides. When we talked about expanding log statements, we said powers can move out front and then be multiplied. So the left side could be written as x times the log of 4. That has to equal the common log of 15. But log of 4, common log of 4, is just a number. We can divide it over to the other side. So x would equal the common log of 15 divided by the common log of 4. So grabbing our calculators, we're going to take the common log of 15. Remember to close off your parenthesis. Divided by the common log of 4. And we've got an answer of about 1.95. Okay, so that's one way of thinking about that question. So I'm going to rework this one. 4 to the x equals 15. We can take the log of both sides, but instead of using base 10, which is what I did in the first time I went through this example, we could choose to use a base that makes sense for this problem. And since 4 is the base that's being raised to the power, we could take log base 4 of both sides instead of log base 10. Now on the left side, log base 4 of 4 to a power, if you remember our log rules, this simplifies down to just being an x, because 4 to the x power has to give you 4 to the x power. On the right side, we've got the log base 4 of 15, and we can use that change of base idea to say this would just be common log of 15 divided by the common log of 4. So you really end up with the same result as what we just did in the first time through this example. It's just a slightly different way of looking at it. All right, so let's try on this one. If we take the log of both sides, we've got log base 10, since we're using common log, of 10 to a power. So this simplifies down to just being an x. On the right side, we need to take the common log of 120,000. So again, let's grab our calculator. Common log of 120,000. And we have an answer of about 5.079. All right. Go ahead and pause the recording and try number 3. Okay, let's check. If we take the log of both sides, now notice I'm just using common log here. I'm going to have to think of moving that power up front because this is log base 10 of 5. Those numbers don't match. So I'm going to bring the x to the front times the log of 5 equaling the log of 134. And then I'm going to divide the log of 5 to the other side. You could have used the other technique. You still will end up in the same spot. So if you had done log base 5 of 5 to the x, you would have had the right side being log base 5 of 134. This side turns into just an x, and this side ends up using the change of base and getting to the same place we're at. So calculator, log of 134 divided by the log of 5. We have an answer of about 3.043. All right, notice on the next couple, we have a little bit more we want to do before we can deal with the power. So in this first one, I'm going to add 3 to both sides. So 40e to the 0.6x equals 240. And then I'm going to divide that 40 out. I really want to isolate what's being raised to the power. And in this case, the only thing being raised to the power is the e. So we have e to the 0.6x equals 6. Now I could do common log of both sides, or I can do natural log. Since there's an e in the problem, it kind of makes sense to do natural log. So we're going to take the natural log of e to the 0.6x equals the natural log of 6. But on the left side, the natural log of e means log base e of e. So our answer is just our power. So to get our answer to this one now, we're going to have to take the natural log of 6. We'll let the calculator figure out what that is. And then we're just going to divide out that 6/10, 0.6. So natural log of 6, close off your parenthesis, and you're dividing just by a plain 0.6. So we end up with 2.986. All right, go ahead and pause the recording and try this last one. All right, checking. First thing I would do is I would add the 5 to the other side. So 7 times e to the 2x would equal 63. Then I could divide the 7 out, and I have e to the 2x being a 9. Now I'm going to take the natural log of both sides, since I'm using e as my base. Natural log of e to the 2x is just 2x. I don't know the natural log of 9, but our calculator can help us get that. So the natural log of 9, and then we'll divide out a 2. So natural log of 9, and then dividing by 2, we should have an answer of 1.0986. All right, so once again, you're going to do 2 types of questions. The first type was where we got a common base on both sides. The second type is where we had to use logs. We took the log of both sides to help us solve for that exponent. All right, so you guys are going to do page 489, numbers 1 through 40.